So what we want to study about the elliptic measure is the A infinity absolute continuity. So what is the A infinity absolute continuity? So it's a bit stronger than absolute continuity, but it's quantitative and scale invariant and mutual also, actually. So we want, if the measure of one set is small, then the measure of if a set is small under one measure, then it's small under the other measure too, in a quantitative way. So what we want to know is, when do we have that the harmonic measure is absolutely A infinity absolutely continuous with respect to, well, the surface measure or the Hausdorff measure on the boundary. So we want to look at the condition on the set omega and the condition on the operator. So let's introduce some definition first. You probably have heard of it already. So the alphas, we said that a set is alphas regular of dimension d if there exists a measure which is supported on E for which all the ball on this set is equivalent to RD. So since divAΔ is not here, I can also say that this set is this condition is often called the Alphas-David regular condition. So let's talk about, so what condition do we need on the domain to have the A infinity condition on the elliptic measure? So we take the Laplacian. So first, we don't look at the operator, we take the Laplacian. And we say that the boundary is alphas regular of dimension n-1. And I hope I'm not mistaken, but the A infinity condition on the surface measure is equivalent to, when the operator is a Laplacian, is equivalent of the fact that the domain is semi-uniform and the boundary is uniformly rectifiable. So many people work on this topic. So I place a few names here. So please don't get offended if you're not on the list. Please don't get offended if you're not in the right list either. So it just, for me, it was just some splitting to organize my thought a little bit. So you have some first result on the plane, on the complex plane first, that use some complex techniques. And then the first contribution outside of the complex plane is due to Dahlberg, and it proves the A infinity absolute continuity of the harmonic measure when the boundary is Lipschitz. And so the optimal result, so you have some intermediate result when the set is one-sided NTA, no, two-sided NTA, and the final condition is a combination of many people that you see on the list, and I don't want to be too mistaken, so I will not say it. But I think it's Hoffman, Martel, Uriatuero, Azam, and Tolsa, more or less. Sorry. So
for that particular case, I think it's more Steve.
oh, Steve. Yeah.
And well, the semi-uniform for the semi-uniformity, I think that Jonas is the one that
Yeah.
exact.
So there is actually many variants. So in particular, there were great work. Instead of looking at the A infinity condition, which is a bit strong, people look, for instance, at the weak A infinity, and you have many other people. So, okay. So a few pictures to see what I'm talking about. So if you've never heard of it, what is a uniformly rectifiable set? Well, it's a set which is well approximated by plane at any point and any scale. So for instance, you have the spiral, well, the weight set in the second case, and for instance, any union on portion of Lipschitz graph will be also uniformly rectifiable. So a set which is not uniformly rectifiable is the four-corner counter set, which you see the first step of the construction here. So all the sets here are of dimension 1. And semi-uniform, so from my understanding, is a set where all the points in the boundary are well connected to the point inside the domain, in some sense. So if you take a point on the boundary here and a point on the domain not too far, you can connect them with a path which is not too long. And the opposite, this one is not semi-uniform because if you take a point which is on the boundary here and a point which is inside the domain above the dark line, then to connect the two, you have to go around. Well, so I don't want to use the mouse anymore. Well, you have to go around all the black line, so we'll take a long path. So this was for the domain. So what about the operators? So the operators are always on divergence form, so in the form minus divergence A gradients. So what about the condition on the gradient? So we have positive results. So the positive result when the coefficient, so when the domain is the half plane, T is the vertical direction, and A is a coefficient that doesn't depend on T. So we have also positive result when A satisfies some Caleson condition. So what is a Caleson condition? I will introduce the definition later, but you need to think that something that satisfies a Caleson condition will be something which is small in some sense. So will be small in a lot of places and in a quantitative way. So why is not surprising? Because uniformly rectifiable, you can characterize uniform rectifiability using Caleson measure and this condition like this. So you have domain which are uniformly rectifiable that works really well with this kind of Caleson measure. So it's not too surprising that the range of the coefficients that are well suited to the absolute continuity are related to Caleson. So the two types of Caleson conditions that you have is that the oscillation of A are close to 0. And if you have one operator that you know already, that you know that it's A infinity, for instance, T dependent, and you make a small perturbation, small in the term of Caleson, then it will still be the harmonic measure of the perturbation, the perturbation will still be A infinity. So taking the Laplacian of this kind of specific case is important because there exist counterexamples. So we cannot take any operators. You need to be aware that there is some strange case. For instance, you can have some cancellation between the geometry of the domain and the coefficients. For instance, if you take the four-corner counter set, which I said is not uniformly rectifiable, then you can take some coefficient A, so that's, well, the harmonic, the elliptic measure is actually equivalent to the surface, the Hausdorff measure. So it's a very nice case. So the next step is we want to, so with my co-authors, divAΔ and Svitlana May-Borota, we asked the following question. Well, uniform rectifiability works not only for a set of codimension 1, but also for any dimension. So what happens if we take a set of low dimension, and then we take the domain which is the complement of this set, and we try to study some elliptic measure on, well, the boundary of the domain, which is the set we take at the first place. And if we can have some characterization of uniform rectifiability using the harmonic measure also. So first, note that this is not possible if you just take the harmonic measure, so the elliptic measure associated to the Laplacian. And the reason is, if you take a Brownian motion that starts at x, then you will have probability 0 to hit the boundary, which is too thin. So what you need the Brownian motion, which is attracted to the boundary. And to construct a stochastic process which is attracted to the boundary, one way to do that is to take some elliptic operators which are elliptic with respect to a weight which is degenerate. So I take a set of my domain, which is a complement of a d-alphas regular set, with d which is smaller than n-1, and I take my operator, which is elliptic and bounded with respect to the weight, which is the distance to the boundary, to the power 1 plus d minus n. So when d is n-1, the power is 0. So you get the classical case. And if we take those operators, then we can have basically all the basic elliptic theory that you have for the classical uniform elliptic operators. So for instance, you can using some weighted Sobolev space, you can define a notion of trace on the boundary for some Sobolev space with the weight which is here. So you can construct solutions, and you can prove that the solutions are continuous. They're continuous inside, of course, because the weight is non-degenerated inside, but it will be also continuous up to the boundary. You can construct green function, elliptic measure. You can compare the function with a comparison principle. So all the tools that exist can be translated. So next, we want to know if we can, for uniformly rectifiable set, if the elliptic measure is A infinity, so we take a uniformly rectifiable boundary. The domain is a complement, so you need to remember we cannot take every operator. So in the codimension 1 case, in the previous case, so it works when we take the Laplacian. It works when we take some t-independent operators or something related to Caleson measure, but we could not take any operator. So our choice of operator, which we think could work, is something which is written minus divergence times d to the power as before, times gradient. So d is a substitute to the distance. So in particular, d is equivalent to the distance to the boundary, but it's much smoother. So it doesn't, it's infinity inside the domain. So for this set and for uniformly rectifiable set, using these operators, which is constructed for any set, any alpha divAΔ irregular set, then we prove that elliptic measure constructed from this operator is A infinity with respect to the Hausdorff measure on the uniformly rectifiable set. So, okay, it's good. Now we want the reverse. So the reverse is much harder, and actually it's false. Because there is a counterexample from Guy David, Max Egelstein, and Svitlana Mey-Boroda. So you have a value, which we call the magic alpha, which is n minus d minus 2. So if n minus d minus 2 is bigger than 0, then the distance is a solution of the operator. Okay, so what does it say using the comparison between green function and harmonic measure? It says that the elliptic measure is comparable to the surface measure. And this works for any set. So we cannot get, comparables mean A infinity in particular, so we cannot expect the reverse. But this is a very particular case, because if you note, so here, so if you note, so nobody can see me if I wrote on the board, right? Okay.
Well, maybe if you already say it, you will see a bit there, but
no, it's fine.
They will see nothing, not very big.
So what happened is L, so this quantity will be the Laplacian of, well, the integral that you have defined with some certain power, which is 2 minus n, I guess. Okay, so you don't have any, so just the Laplacian of the integral. So you permute them, and you realize that the Laplacian of this guy, the Laplacian, so in x, it's just 0. So it's automatic. So the proof of this result using, so this counterexample is bad, but there is something good about it. And the good thing is that there exists a short proof of the fact that the elliptic measure is A infinity. So here I wrote the Carousel measure, what I call the Carousel measure condition. So we ask that f is, so when you integrate over a 10 set, where there is not too much place where it is big. So it's something which is close to zero, as I said. So first step, if gamma is uniformly rectifiable, then the gradient of the quotient between the distance is a Carousel measure. Satisfies the Carousel measure condition. Okay. Then, well, basically, you say that the first operator, so L beta, is D. So the one operator with beta is a kind of perturbation, a Caleson perturbation of the second operator with alpha 0, the magic alpha. Since you know it works with alpha 0, and the second operator is kind of a perturbation of the first one, then you can know that the elliptic measure will be A infinity without going through too much computations. So after this, we struggle a little bit. So we thought, okay, instead of working with the harmonic measure, why not work with the green function? Because the harmonic measure and the green function have some kind of dual properties. So if we can say something about the harmonic measure, we should be able to say something about the green function. So the idea is to say that the green function is close to our smooth measure, smooth distance. Because we know that we have some magic alpha. We say that the green function, what we call the green function with pole at infinity, so it's kind of a special green function, will be exactly the distance. So there is we didn't see much result before. So we find some result of Hoffman, Martel, and Toro about some estimate on the second derivative of G, but the condition on the operator, which we're not too happy about it. And the reason is we want operators, the same operators than the ones that we know, the same operators than the one we have for the absolute continuity of the harmonic measure. So we call them the weak DKP operators. So it's operators for which, so I like to write them like this. The coefficient can be decomposed into two parts, a B and a C. So the oscillation of B are bounded, are small in terms of Carousel measure, and you have an error term, which is C, which is small in terms of Carousel measure. So these operators, you basically know that for those operators, you know that the elliptic measure is A infinity with respect to the surface measure. So you want a result on the green function for the same operators. So in codimension 1 and higher codimension, you have some estimates. So for those operators given by divAΔ, Lee, and Svidlanami-Boroda. So there is a mistake actually, sorry. So you see that G is more or less the distance to the boundary. So if you are in the upper half plane, the distance to the boundary is just T. So you compute the gradient of G minus lambda times the vertical unit gradient, not T. So gradient of T. And this is a Caleson condition measure. Yeah, I'm almost done. So in parallel, we try to have some kind of fun using the magic alpha, the same thing. We prove another result, which is if you take a green function, so yes, what we call green function is a function which is a solution inside the domain, which is 0 on the boundary and which is positive. So that everything which is written here is well defined. So this quantity is a Carousel, satisfies the Carousel condition, which means that the oscillation of G and the oscillation of D are kind of close. And for this result is actually, so we use the magic alpha, kind of. We use the fact that, the operator with beta is just a perturbation of the operator with the magic alpha, and it works pretty smoothly. We had to use in the midtimes the fact that the elliptic measure is A infinity anyway, which is a problem for the last part. So we say, okay, we got it in higher codimension, so it should be true in codimension 1 too, right? Hopefully. So we try, and we succeeded also. So we don't know exactly the best condition. So we know that if gamma is a Chord-Arc domain, so what we use that the boundary is uniformly rectifiable and you have enough connectedness inside the domain, so Harnack chain and cross-group point, then you have the same result for all operators which are with DKP, with DKP stands for Dahlber-Kenig-Pipher. And well, our condition about the topology, so the cross-group point, the Harnack chain, comes from the fact that we use the A infinity of the elliptic measure. So we are trying to see if using a stronger result with weaker assumptions, we will be able to improve this result a little bit. Okay, well, thank you very much.